Hello everyone. In my previous video, I talked about one of the important operations on an image, which is binarization, right? Converted into black and white, zeros and ones, which we learned we can do using a threshold, comparison of the light intensities against a threshold. Bigger than the threshold, we can call them 1, less than the threshold, we can call them 0, or vice versa. So the major question that came up was what threshold should we use, right? If you have to choose a threshold, right, what kind of threshold, how much is a good threshold? So the first thing is, what is a measure of goodness? How do we decide goodness? So let's say here, if I show you a couple of pictures, here is one picture I recently took for one of my previous videos for maximum range detection in a camera. Here is a ruler against some carpet. And if you look at the histogram of this image, the distribution of light intensities in different values, the frequency of them, you clearly see two modes, right? You see that the distribution of this light intensities is kind of bimodal, right? Oh, sorry. This here is the darker area, which has a lot of pixels, and here are the brighter areas, which has fewer pixels. So clearly you can say this is the ruler in this case, and this is the rod. Right? So sometimes the boundary between them is quite clear. If you look at this area for the areas between them and then the areas less than the average of the carpet value, you literally have very, very small frequencies. So you can clearly see this is a bimodal distribution. A very good bimodal distribution. In those cases, if I want to exactly break it into two parts, a foreground and a background, or a part 1 and a part 2, it's not the hardest thing to decide. You might roughly say any number here between the two modes, which is somewhere like here, that could be a good threshold, because it clearly separates the two peaks. Now, still in this range, which is for here somewhere between 180 to like 210, some of the thresholds do a little bit better than the rest of them, but the performance does not improve or drop significantly. Correct? Sometimes for some images, the bimodal distribution is not as clear. Here, if you look at this picture for the horse, you clearly can see that you have a lot of dark pixels here, and then here you have some white pixel. But here the difference between the two peaks is not as obvious as the previous case, because in the previous case you clearly had two dominant modes, two dominant peaks. In this case, only one of them is really dominant, the other one is kind of flat. And then between them there is this plateau. Between them there is this plateau area where you have a range of what? Light intensities. So the question is, yes, I know the threshold should be somewhere here, but where? Should it go all the way toward, let's say 70 or something, or come all the way here toward maybe 170, right? So here you have 100, a range of 100 for the threshold to choose, while here it was something like 30. So the wider that you can choose, the bigger this plateau is between the two modes, and the flatter one or two of them would look like compared to the plateau, it makes it harder to decide on this threshold. So the question is there any way that we can decide? And the answer is yes. If we consider this problem to be a clustering problem, so breaking the problem into, or the whole set of data in the image into two clusters. Cluster 1 is called the foreground, and cluster 1 is called what? Anything else, literally is like the background. So you're doing a clustering problem. The question is, what kind of threshold is good? So these two clusters are good clusters, and we have done a good job in clustering if the data belonging to each cluster are very close to the center of the cluster, right? So for example, here by center, I don't mean the physical center, I'm talking about the histogram. So if this red is one cluster and this is like the center of the cluster, if all of these data in this cluster are close to the center, in other words, the standard deviation or the variance of this cluster is not so big. So this is like sigma of, in this case, the foreground. And this is the mean value of the background, or actually that was the background because that's the darker area. And this is like the average of the foreground pixels, and this here, that's not exactly sigma, it's like 3 sigma if we consider it like a normal distribution. So we say something like, let me draw something nicer. That's an indication of sigma, but that's not sigma. So like here, for example, say this is like 3 times sigma background, and then this distance here is like 3 times sigma foreground. It's a good threshold if it makes this sigma foreground and background as small as possible. But how do you combine? Because you want both of them to be small, so a good way is to simply add them together. If I can add these two sigma foreground and background and minimize that function as a function of threshold, that is a very good function to optimize. The only problem is these two peaks, they do not carry the same weight. If you look here, the background carries a lot more pixels than the foreground. Look at the frequency values. So the sigma of the background here, which carries, it is calculated for a ton of pixels, it is a good idea to multiply that sigma here by all of those pixels contributing to it. The same way, multiply sigma foreground times the number of pixels contributing to it. That's where here you see we multiply them by their corresponding number of pixels or number of frequencies, some of the frequencies. And this is what we call the total between or within cluster variance. Because each one of them is one of the sigma background, foreground, or for inside, within the cluster. And when you add them by weighting them with their number of pixels, this is a total within cluster variance. Clearly, this is a function of what? This guy is a function of that threshold. Why? Because if I move this threshold to the left or to the right, then a bunch of these pixels would be allocated to the peak or the distribution of foreground. A bunch of them will be belonging to distribution of the background, and that changes their sigma, right? Because now let's go look at this case. This might be a little bit nicer to see. So now if I put my threshold right here, let's say, then all of this data from here to here are going to be what? My background. So first of all, this data that you see, I cannot call it a normal distribution anymore. It's a skewed clearly distribution, but this one has a sigma. And then this other portion from here to here, this one also has a sigma, right? Which you calculate. But now if I move it and let's say I bring it here, then what's going to happen? Then the data that you have for the foreground is going to be only this, and for the foreground is going to be all of this in black. You see? That's the big difference. You're clearly, by moving the threshold, you're either growing the foreground against the background or growing the background against the foreground. You make one of them to contain more pixels. You're tilting the scale toward one of them. And that clearly makes their sigmas bigger or smaller and the number of data belonging to each category. So the question is, which one of these thresholds will bring that total function down? That can be the best threshold that we can choose for binarization of the image. And if we do it by optimization, then this is automatic threshold selection for image binarization, not just you manually think, hey, I want to choose 50 or 100 or 200 or something. So that's where in the command image to BW, if you don't pass to it a threshold, because you can pass to this command a threshold. If you don't pass a threshold, then it tries to, by default, select some number. How? This can be one of the best ways that it can do it. Bring down the total within cluster variance. How do you do that? Here, I'm going to show you in the code. So here, I have written a very simple code that when you select your image, here I show you the image, I show you the histogram of the image, just these two that you can see, and then I choose a threshold range from 5 to 250, so almost from black to all the way white, and I change this threshold 5 at a time. So threshold goes from like 5, 10, 15, 20, 25, all the way to 200 and what? 50. I don't go for 0 and 255 because in those cases, definitely one of the two clusters is going to be non-existent, empty. So I go from close to 0 to close to 255. I change threshold so much each time. You can only change it 1 if you want at a time. It just makes the computation more. But this gives you a rough idea of where the minimum is. Where is the minimum of that total within cluster variance? So what do I do? Here I convert all of my image into a line vector using vectorization. And then I go for each one of the values in that threshold. I use the command find and find the indices of those locations in this vectorized image for which the pixel values are less than the threshold or equal to the threshold, or they are bigger than the threshold. If they are bigger than the threshold, I call them indexes of the foreground. If they are less than or equal, I call them indices of the background. So now I read those values of the background, I convert them to double, and I call them the background cluster. I read the vectorized image at the indices of foreground, I convert them to double, and I call them foreground cluster. I say if any of these two clusters is empty, then the total sigma that you calculated for it, call it none, because it doesn't exist. This variance only exists when both clusters do exist. If one of them does not exist, so all of your image becomes foreground or all of it becomes background, this has no calculation. And here you see I multiply the number of pixels using the command length by the standard deviation of that cluster, and then do it for the foreground, background, add them together, and I call it the total sigma I, and then later I plot that sigma against the threshold to see where the minimum is. Again, if you want, you can change this one at a time. It takes more computation, but it's a brute force search to find at which threshold the total within cluster variance is minimal. Okay, you might say, why did you do double? Because the command std only works on the data that are double. If we leave them without double, then background and foreground are going to be uint8 data, and the command std is not going to work on them. So that's why I used std. And I'll share this with you under the video description. I'll share this code with you along with the images, the binarization image, or maybe the horse image, or both. Maybe I share it with the horse image. It looks nicer. And then you can see the plot. So let me go ahead and do that, run it for you for the ruler example. So this is the image. If I look at the histogram, as I said, it's a very clear bimodal distribution. And if you use data cursor, clearly something in this range, somewhere from, you see 180 to maybe 205, 204, a range of 25. Any number in this range can be a good choice. Which one of these do we decide? Here I can look at this graph that I told you. This is the graph of total sigma within cluster variance versus threshold. And if you use your data cursor or use the command min, you clearly see the min. If you look here, this is 181.11, 181.18, goes up, and again 181.56. So the minimum is at 185. That is the best threshold to choose for this image. That brings that variance to the minimal. And here I'm showing you some samples. This is the original image. This is threshold in it with a threshold of 30. If you see, you clearly don't see anything. Every part of the image is foreground. If you do AD, it's almost the same. It barely detects any foreground or background. If you look 115, now I'm using out of all of those numbers I calculated. Remember here, when you go from 5 to 250, correct? The range is 245 divided by 5, and you're looking at close to 50 data points. So I evaluated sigma at 50 data points, but here in this last plot, I'm only showing you 7 of them. 185, the minimum, is one of them. But clearly, if you look, 30 and 80 are definitely telling you no good thresholding number. 115 start to distinguish. 150 is doing quite a bit better. Now you can see the ruler. 185 is close to perfect. Look at that. And if you zoom here, right, you can see almost the entire ruler, and everywhere else is black. So that's a very good clustering, very good foreground background separation. Here 210, which is a little bit out of the minimum range, is not too bad either, but you're losing a bunch of pixels, right? If you look here, you see there are a bunch of black pixels from the ruler that you left out as background. Here you barely miss any. And once you go to very high numbers, now you literally detect everything as background, which is again not correct. So clearly you see why 185 is a good choice, right? Because it does the best job in separating foreground and background here, right? So clearly you see that was a very good choice. Similarly, I can do it with the horse. In the horse case, the separation of the two modes, as I said, is not as clear as this one. Let's take a look. So here, if you look at the histogram of that, clearly, as I told you, there is a plateau between them, and this mode here is not dominant. So selecting a number anywhere from, let's say, 80, 70, 80, all the way to 174. It's a range of 95 to 100. Selecting a number in between is not necessarily the easiest thing unless I look at that graph. Here is that graph, and again, here, if you look at the minimum data, you see 75 is a good number, and then if I move 75, correct, you see 166, 164, 164, 500, so 80 looks like a good one. 80, 5 jumps up. So 80 here, as you can see, is your minimal of the graph. So if I can use 80, that's probably the best threshold here. And here, one of the sample numbers I chose for this image is also 80. So for the previous one was 85, the minimum for this one is 80. So this last graph should also work here. And if you look here, again, look at that, 30 does not distinguish well. 80 is very good. Actually, 115 comes close to it. 150 is not bad either. 185, you're clearly missing a bunch of the horse, and 210 and 235, you're losing a lot of it. So between 80, 115, and 150, which one are good? Well, clearly, if you look in 150 and 115, a bunch of the pixels on the legs of the horse are missing. Especially in 150, it's quite clear the two rear legs of the horse are missing. The only place that you can see the legs of the horse very clear are about 80. Now at 80, you see a little bit more of the background are clustered or classified as foreground. What are they? They are the reflections on the ground, as you can see here, and a little bit on the leaves. Okay? Now in real life, when you do classification, this is not exact, we are not doing classification here. When you do want to do clustering on an image, or segmentation is what you really call it, not only you have to look at the light intensities and say, hey, those light intensities closer to each other are one object, the rest of them are one object. No, you also have to look at spatial proximity. How close are their U and V pixels? I mean, these pixels that belong to the horse, they can be one object, but these are that are separate and very small, they probably are a separate thing. Okay, so if you later you really want to do segmentation, you should not only look at the light intensity as we are doing right now. You have to look at the spatial proximity and a lot of other things. But again, the goal here is not pure segmentation. Is just to use a threshold. If I want to say one range of light intensities is foreground and one range of light intensities, the other part of the histogram is background, where is a good place to put that threshold? Here you clearly can see 80 is a good place to go. 115 is not too bad either. You have not missed a lot of the horse. And if you look at that graph here, this graph, 115 is not far away from the minimum. I mean, let's take a look at this. Let me run it again. Clearly you see, if you look at the graph of sigma versus threshold, this is your 80 here, right? This is your min, but if I bring 115, let me add another one. Okay, it's not so far away. I mean, it's not as minimal as that, but the difference between the values, total cluster, between cluster values between these 2 points are not so big. So probably if you come here on this side of it and choose another data point, maybe 65 or maybe 60, that should also be quite as good as 80. Because here you don't have a deep hole as minimum, you have a smooth transition. Okay, so if I add 60 here instead of 30, let me add 60. Right, let me just change this number to 60. That should not be the worst case of all as well. Let me show you that here. You see, that's your 60. It still keeps all of the horse. The only problem is now it also detects a lot more of the reflections as the foreground. Clearly 80 is doing a lot cleaner job compared to 60. 115 is detecting even less reflections, but at the cost of what? Missing a bunch of pixels of the horse. So going from this extreme to this extreme, I would say 80 in between could be a good threshold. And that's what that graph would tell you. Okay, so hopefully this demonstration was useful to you. If you ever wondered how MATLAB would decide on a good threshold for image binarization, I would say this: minimizing the total within cluster variance is a very good way. Hopefully the video was useful to you. I will see you in next video. Thanks.